Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and as always, I'm joined by my brilliant co-host, Victor. Before we dive in, I'd like to remind our listeners that your support means the world to us. If you're enjoying the show, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you.
That's right, Sheila. Your feedback fuels our passion for sharing knowledge about decentralized systems. Now let's jump into today's topic, shall we?
Absolutely. We're currently in Season 1, Chapter 4, discussing decentralized storage systems. Today we're exploring a fascinating concept called eventual consistency. But before we get into the nitty-gritty, I've got a brain teaser for our listeners. Here's the quiz question. In which popular social media platform might you experience eventual consistency when liking a post?
Ooh, that's an intriguing question, Sheila. It's something many of us might have experienced without even realizing it. I'm curious to see if our listeners can identify this everyday example of eventual consistency. While they ponder that, let's set the stage for our discussion. We've talked about strong consistency in our previous episode, so this should be an interesting comparison.
Great point, Victor. Before we dive deeper, could you give us a quick refresher on what consistency means in the context of distributed systems?
Certainly. In distributed systems, consistency refers to how data remains the same across multiple nodes or replicas. Strong consistency, which we discussed earlier, ensures that all nodes see the same data at the same time. But today we're looking at a different approach: eventual consistency.
Interesting. So, what exactly is eventual consistency?
Eventual consistency is a model where the system guarantees that given enough time, and assuming no new updates, all replicas will eventually converge to the same state. In other words, if we stop making changes to the data, all copies of that data will eventually be the same across all nodes in the system.
That sounds less strict than strong consistency. Can you give us an analogy to help visualize this concept?
Certainly. Think of eventual consistency like a group of friends sharing gossip. When one friend learns a piece of news, they start telling others. Those friends then spread the word to more people. Eventually, given enough time and no new gossip, everyone in the group will have the same information. However, at any given moment, some friends might have outdated or incomplete information.
That's a great analogy. It makes me wonder, why would we choose eventual consistency over strong consistency? It seems like strong consistency would always be preferable.
That's an excellent question, Sheila. The choice between strong and eventual consistency often comes down to a trade-off between consistency and availability, which is part of the CAP theorem. The CAP theorem states that in a distributed system, you can only have 2 out of 3: consistency, availability, and partition tolerance. In distributed systems, especially those operating at a large scale, it's sometimes impossible to have both perfect consistency and 100% availability. Eventual consistency allows for better availability and performance in many scenarios.
I see. So, in what real-world scenarios might we prefer eventual consistency?
Great question. Eventual consistency is often used in systems where real-time accuracy isn't critical, but high availability and low latency are important. Social media platforms, like the one in our quiz question, often use eventual consistency. Other examples include DNS, domain name system, updates, email systems, and even some e-commerce inventory systems.
That's fascinating. It sounds like eventual consistency is quite common in systems we use every day. But I'm curious about the challenges. What are some of the pitfalls developers should be aware of when working with eventual consistency?
The main challenge with eventual consistency is handling conflicts that can arise when different nodes have different versions of the data. Developers need to implement conflict resolution strategies. Another issue is that applications and users need to be designed to handle temporarily inconsistent data. It's also crucial to understand and communicate the expected convergence time, how long it typically takes for all nodes to reach a consistent state.
Those sound like significant challenges. Are there any best practices or tips for working with eventual consistency?
Absolutely. One key practice is to design your system to be conflict-resistant where possible. For example, using data structures that are naturally easy to merge, like CRDTs, conflict-free replicated data types. It's also important to have clear policies for conflict resolution when it does occur. Additionally, providing users with indicators of data freshness can help manage expectations. And of course, thorough testing of various consistency scenarios is crucial.
That's really helpful, Victor. You mentioned CRDTs. That sounds like an interesting topic for a future episode. Now, speaking of future topics, I think it's time to reveal the answer to our quiz question. The social media platform where you might experience eventual consistency when liking a post is Facebook. Have you ever noticed that sometimes the like count on a post seems to fluctuate or doesn't immediately update? That's eventual consistency in action.
Exactly right, Sheila. It's a great example of how eventual consistency allows platforms like Facebook to prioritize availability and performance while still providing a good user experience. The temporary inconsistency in like counts is usually not critical to the user experience, making it a perfect use case for eventual consistency.
To wrap up, let's summarize the key points we've covered today. Eventual consistency is a model where all replicas of data will converge to the same state given enough time. It's often chosen over strong consistency to improve availability and performance, especially in large-scale distributed systems. While it comes with challenges like conflict resolution, it's widely used in many systems we interact with daily, from social media to DNS. Remember, if you're implementing eventual consistency, focus on conflict-resistant designs, clear resolution policies, and thorough testing.
Excellent summary, Sheila. I hope our listeners found this deep dive into eventual consistency enlightening. It's a crucial concept in the world of decentralized systems and distributed databases.
Thanks, Victor. And thank you to all our listeners for tuning in. If you enjoyed this episode, please don't forget to visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us continue creating valuable content for the developer community. Until next time, keep coding and stay decentralized.